Okay, so hello and to all the audience of this podcast, thanks a lot for your interest. I am Davala. I am a postdoctoral fellow at Technical University of Munich, and with me Shreya, who is an engineer at PRL Ahmedabad. In this series, we will be talking to women scientists and educationalists who have contributed to the community, and they have a story to share with us. So, the message we are trying to emphasize is that any of you listening to this podcast and wants to pursue science or academia as your career, you can do it, and there's a lot of interesting stuff out there. So, the experiences of the people with whom we talk serve as a guideline to shape our thoughts and also to enable us to make informed decisions in crucial points of our life. So that's the whole idea behind this series. Today, we are talking to someone whose wisdom spreads across various aspects of science. She is Shobhana Narasimhan. She is a theoretical physicist at Jawaharlal Nehru Center for Advanced Scientific Research, which is an elite research institute of India based in Bangalore. She is not only a great scientist, but also works for the community of scientists, women in particular. So a lot about her can be found online, on Wikipedia, everywhere. I don't want to repeat it. But a couple of facts that really stands out to me is that she is recognized as the Fellow of American Physical Society. This is a signal honor for any physicist. She's also recognized as a Anna Boyskin Fellow at the Institute of Advanced Studies at TU Munich for her work and for women in science in general. So without much ado, let's start and talk to her and learn more about her path. I'll kind of shuttle in between Shreya will lead this conversation, and up to you, Shreya.
Okay, so hi, ma'am, and thanks a lot for joining us today. So
I'm very
maybe,
happy to be here.
and so ma'am, maybe perhaps we can start with a very fundamental and like the starting question. So maybe we can talk about your childhood, and you can tell us what was the atmosphere like while you were growing up, and what was your childhood like? Yeah.
Okay, so I grew up in Mumbai, which was then called Bombay. And my parents, my father was a well-known mathematician, MS Narasimhan, and my mother is Shakuntala Narasimhan. She's also pretty well-known, both as a journalist and as a musician. So she actually was doing her PhD in economics when she got married, and she couldn't continue in that choice of profession because of the constraints imposed by marriage and motherhood. I was born about a year after they got married. And so I think I was always aware of that, the limitations placed on women by their circumstances. And I was always encouraged by both my parents to follow whatever interested me. It was a house with lots and lots of books in it, thousands of books. So I always enjoyed reading a lot. I have a brother. He's almost 7 years younger than me. And I went to a convent school, a Catholic school, Convent of Jesus and Mary in Mumbai, which is also called Fort Convent. And that's a girls' school. And in this school, I was never made to feel that there was anything I couldn't do just because I was a girl. We were totally encouraged to follow all our interests. And I was interested, I would say, in pretty much everything. I was interested in history, geography, art. I didn't feel that there was something that appealed more than everything else. I knew that I really, really liked reading. I was always very good at English, but I was also always very good at maths. And till till my 10th standard or so, I really didn't know whether I would follow a sort of path where I would study the arts or study science, because both really interested me. And I think I was good also at both. But the interesting thing is I didn't really like physics, and I would never have dreamt that I would become a physicist. So that's the short summary. You can ask me about more aspects of this if you're interested.
Yeah, I mean, so one question that pops up is like you mentioned, and we've also read about this, that both of your parents were quite known and well renowned. So growing up in a house which had like which had parents which were already so, quite known and people knew about them, did it create some kind of pressure on you, or any kind of imposed expectations from the people around you, in some sense that might have been a bit difficult, or not even difficult, maybe a good thing as well in life, something significant?
Yeah, so I think it has both advantages and disadvantages. The advantages is that I happen to be very interested in both their subjects. And so I was interested in writing, I was interested in maths and science, so I was really encouraged to pursue these interests. But of course, they had very, very high standards in both these things.
Exactly.
And though they never explicitly said you have to do this, so you have to do well in school or whatever, I felt it implicitly. I felt this pressure to encourage and to live up to their standards. And I would say I'm somebody who doesn't have much self-confidence. And I think that is because of growing up with such high achieving parents, because I always measured myself up to the standards of their achievements. I think that's partly why I didn't go into mathematics and chose physics. I mean, that's not the whole reason. I did really, as I said, I started out not liking physics, but at some point I really discovered physics and fell in love with the subject. But I always was hesitant to go into mathematics just because my father was in mathematics and I didn't want to be in the same field, even though I felt I liked it and I was good at it. But I was very aware of this reputation of my father, and this feeling that I was known as his daughter, and I didn't want that hanging over me. I felt I had to live up to too much. And so I really didn't want to go into the exact same field. Like when I went into college, for example, my maths teacher, some of them came to me and said, "Oh, we're so honored to have you in our class. It's such an honor to teach Professor Narasimhan's daughter," and things like that. And I really didn't like all that.
Of course, I mean.
But was it, but was it because they just said it inherently, or was it like you were so good that they sort of said, okay, you have to be so good? Was it that?
It was probably a bit of both. I mean, also because I would do well, then I remember once I didn't do so well in a maths exam, and the teacher came and told me, I get very depressed when I correct the answer sheet. So this time I searched through the whole pile and I started with your answer sheet because I knew you would have done well, and then I would feel good. And then this time you didn't do so well. So what happened? So then I felt I've let down myself, I've let down my teacher, I've let down my father. So I mean, I really didn't like all that. I really wanted to be sort of anonymous, and I couldn't be anonymous.
Exactly. I mean, that's just too much pressure to live with. I mean, I didn't have anything of the sort. I felt so much pressure. I can't even imagine what it would be like to be in those shoes.
And that's also partly why I decided to go to the US to study further, because I did get into TIFR for my PhD, but it was clear to me that I wouldn't want to do my PhD there because my father was a professor there. He was a little upset. I mean, he said, if you want to go abroad, that's fine. But the reason you want to go abroad shouldn't be that you're running away from me. But then even at Harvard, once in a way, somebody would come and say, oh, are you Professor Narasimhan's daughter? And so it was very hard to get away from that.
Yeah.
But eventually, I mean, after years, it turned around, and towards the uh, end, it would be like he would be asked, are you Shobhana Narasimhan's father? So, and then he would feel kind of proud, but also a little upset, I think, that, the balance had changed. But
I
Yeah.
mean, it's also quite difficult because this one side there is mathematics and your mom took over all the arts, so there was no escape for you in both fields in some sense.
yeah, but I really like both. I really didn't know whether I wanted to do arts or science because I really liked them both. And I was really surprised that there was this general expectation that, of course, she's going to do science because she has good marks and she has the marks to get into science. You know how that is in
Well,
India.
yes,
People assume
yes,
that if you have the marks to do science, you do science. And you only do arts if you don't have the marks to get into science or commerce.
Science. Yeah.
Whereas I really liked arts. And then finally, I decided I like writing and I like doing science. And I could see myself as a scientist who also wrote, but it was very hard to see myself as a writer who also did science.
Yeah.
And so that's why I finally decided to choose science.
Actually, there's just a follow-up based on what you said that when you were in schooling, so the options were okay, if you have marks, you do science, else you do arts. An extension of that, I feel in present times, is if you have marks, you do engineering or medicine. If you don't, then you go to sciences, and
Yeah.
arts is
So
not
what?
even spoken of.
Yeah.
So
Yeah.
what happened?
So at 10th standard level, I'm talking about 10th standard. After 10th standard was when we had to decide whether to do science or arts or commerce. And then after 12th standard was when you decided whether you want to do engineering or medicine. And at that point, it was during my 11th and 12th standard that I really started liking physics. And then I was just completely clear that I want to do physics, and I did not even consider doing engineering or medicine. And this is the stage at which a lot of students who really like science face family pressure to do engineering or medicine. But for me, that was totally absent because, to be honest, my parents probably thought that engineering and medicine are not as much worth doing as doing science. So maybe I'm being unfair to them. I don't know, but we just never discussed it. I said I want to do physics, and they said, okay, fine, do physics.
So was it, you said in 12th, you really started liking it. Was it a good teacher, or was it your drive reading some good book, or how did that?
So it was a combination of things. I had some very good teachers. This is when I first encountered quantum mechanics and relativity, and these really started appealing to me. And I started reading up a lot of physics on my own. I also started reading up the history of physics a lot, and that I found it interesting. And so, yeah, I just spent a lot of time teaching myself physics and just really fell in love with quantum mechanics and relativity, especially, I think.
That makes a lot of sense. And yeah. So, ma'am, like, since we are on the growing up and the childhood part, I would like to ask a question which is more related to the general populace. Like, there are a lot of people who are like interested in science and mathematics, but especially when it comes to the 11th or 12th standard, when you're about to get into the real world where you have to, like, get a degree and all of that, there's a lot of pressure of moving into engineering, like already we've talked about, and pure science isn't really looked up as something that can be pursued at that stage. A lot of people, in fact, turn into pure science after they've completed their engineering. So can you give us some thoughts in general, like given the scenario, or what are your thoughts on the subject?
Okay, so first of all, let me just continue my previous answer. It wasn't just my family that valued doing science. See, I grew up on the campus of a scientific institute. I grew up on the campus of the Tata Institute of Fundamental Research in Bombay. And so it wasn't just my own home, but all my friends, all my neighbors, all of them thought scientific research was a fantastic thing to do. And it was really, really valued. And I think in almost all those homes, they would have said it is better to be a scientist than to be an engineer or a doctor. And most of my close friends whom I grew up with in that environment went on to do PhDs in science, regardless of whether they were men or women. In fact, probably more so the women than the men, I don't know. But so it was a very unusual environment I grew up in.
Yeah.
So why do people say not to do science and to do engineering or medicine instead? I think the first thing is people feel you don't have job security as a scientist. That is true a little bit. You're more likely to be employable perhaps with an engineering degree or a medical degree. But a lot of it is also people just aren't aware of the opportunities. Scientists in our culture don't have that much visibility, I think. People don't realize what it means to be a scientist. That's exactly why it's great that you're doing this kind of podcast and blog to tell people what is the life of a scientist like, what are the opportunities for scientists. People just aren't aware of it. And so they all know somebody who's done engineering. Everybody knows doctors because everybody goes to the doctor. So they say, no, what will you do? They say, maybe you can become a school teacher or a college teacher. And that doesn't seem like an attractive enough career option often because the salaries are not so high, etc. And so they don't want their children to go into this. The other thing is, if you want to become a scientist, especially an academic, it's a very long path. It takes years. I mean, after your 12th standard, you have to do a BSc, then you have to do an MSc, then you have to do a PhD, which can take 5-6 years. And even after that, you don't get a permanent job. You have to do a postdoc for 5 years or whatever. So you're 35, 36, 37 before you start getting a permanent job. And that just seems too long to most people. They want you to be settled before that.
That is true, yeah.
And so I think they worry about that. So part of it, I think, is a lack of knowledge, and part of it is that it's just such a long process.
That does make a lot of sense, yeah.
The other thing is also perhaps that you don't have as much mobility. You have to go where the job is. Like as an academic, it's not so easy to say, I want to be in Mumbai or I want to be in Pune. You have to go where the job, where you are able to get a job. If you're an engineer or a doctor, it is easier.
Yeah.
So especially if parents want you to stay near them and they don't, or they want you to be married to somebody and stay in a particular locality, they find all these things of concern, I think.
Yeah, I mean, because if you look at the academic institutes that you'll find around India also, it's only the major cities where you can find them. And there are a lot of places.
That's not necessarily true. They are there all over the country, but they're specialized. So depending on what is your area of specialty, you have to go where your specialization is,
right,
or where a job opens up in your field of interest.
Yeah.
Whereas if you're a doctor, you can be a doctor anywhere.
Yeah, people get sick everywhere. That is true. So I guess at this point we can move a little bit deeper into your research journey. So like we know already now that yes, you were quite inclined to physics, and but physics in particular, of course, has like quite a lot of fields and areas to dive into. But and we know that you work in theoretical physics. So
Mhm.
first, I would really like to ask why theoretical physics? Because to me personally, I'm an engineer. So to me, looking at things functioning helps me understand them better. So I would really like to know how your mind encapsulates the whole idea of theoretical physics, or while you were starting out, what were your ideas and expectations when you were entering the field of theoretical physics?
Okay, so it's kind of a complex question, I think. The simple answer would be that I was just much better at theory than at experiment, I
Okay.
think.
Okay.
I did spend one summer when I was a BSc student working in an experimental lab, doing experiments on laser spectroscopy. And I just felt that this is not something I'm very good at. But just a few years ago, so like, 30, 40 years after I worked in that lab, I met the person under whom I worked. And I said, oh, I was such a disaster in the lab. And he said, no, you were very good. So maybe I judged myself incorrectly. But I remember, for example, some result was just not coming, and it was giving weird results. And we had to spend a lot of time tracking it down. And then ultimately it turned out that there was one little resistor in that circuit, and we had exceeded its power capacity, and that's why everything was going down. And I thought, I can't deal with this. I would much rather that it's some fault of mine which I have control over. But at that time, that's how I thought. Now I think this is also interesting. I mean, this is also like a puzzle that you have to solve. But I think, at least when I was growing up, I don't know how it is now, it's something about our culture that we valued abstract knowledge over practical knowledge. Okay, so I was never really encouraged to, play with things, break apart things, find out how things worked. And I don't think this is just something to do with gender. I think it's something to do with culture. Because in our house, it was my mother who tried to fix things or hammered a nail into the wall or whatever. It was not my father who did those things or changed a light bulb. These were all things that were my mother's province rather than my father's province. But I think we have this idea that, I mean, I still see it now, that I see Indian students, they think the best thing to do in physics is string theory, because they think that is the most abstract, that's the highest you can achieve. And in some sense, I feel there's this idea in India that if something is useful, it is looked down upon. I really wonder if it goes back to our caste system or something, that, working with your hands is not seen as conferring as much status as just thinking with your mind. So I'm not
Higher
saying I
the
had these thoughts explicitly, but I think I had these ideas that, and so what did I want to do? I wanted to do astrophysics, or I wanted to do high energy physics, which is what all Indian students generally want to do. They seem to be the most fundamental, probing the mysteries of the universe, etc. I mean, I'm not saying these are not topics worth studying, but they're not of much use. They're not of much practical use. And to start with, this is the way I thought.
so you sort of find an analogy between higher the caste, then you think, you meditate, or you do so-called higher stuff, and that relates to how the smartest kids kind of choose string theory in difficult subjects, so to say. And
Well,
or if
let me tell you a story. I might have told it to you before, I don't know. But when I was in the US, somebody came and asked me, can I ask you something? What is your caste? And I was very uncomfortable with the question. And I said, why are you asking? And they told me that at their university, uh, after 2 years, the PhD students had to do an examination, and only the students who did best on that examination were allowed to do theory, and the rest had to do experiment. Okay, so that already is something one can question. Why is there this idea? And then an Indian student didn't do very well, and so he was assigned the experiment, and he went and told the professors, no, I am a Brahmin, so I cannot do experiment. I have to be allowed to do theory. And they got scared because they thought they're interfering with some religious
Oh my God.
or something, and they let him do theory. And this person came and asked me, is this true that if you're a Brahmin, you can't do experiment? I mean, this is, of course, an extreme case, and I think the guy was just being extremely manipulative and shrewd and taking advantage of their ignorance in doing this. And I was quite outraged, in fact, when I heard this story. But I think, I mean, this is speculation. I'm not an expert in this, but I do feel there is some connection.
Yeah.
Yeah. But so now having thought of you as the smart one, and then there is the string theory, and then how did you pick the field that you work on, which is density functional theory or computations, which is I mean, it's not what you started off with. So how did you make this choice of the subject?
Okay, so I drifted into it bit by bit, but
Yeah.
I would tell you what initially happened. Okay, I went to Harvard. I was admitted to do high energy physics or astrophysics, and the astrophysicists were just in a different building, so I didn't have that much interaction with them. But I saw the high energy physicists there were extremely well known. You know, some of them had Nobel Prizes, etc. These were my gods before I went there. And I just found them really obnoxious. I mean, so arrogant and so, I don't know, I just felt I couldn't see myself working with them. I was just really uncomfortable with the culture of arrogance and also intimidated by them. Whereas I found the condensed matter physicists much easier, more straightforward, less arrogant. And I thought I want to do condensed matter, but I'm so glad I made that choice, because the other thing that I always struggled with was my sort of social conscience, in the sense that I always felt one should do something that helps people, that contributes something to society. And I used to worry that physics didn't do that to a sufficient extent, or not in a direct enough way. And that by doing physics, I was pleasing myself, my intellectual interests, but not contributing enough to society. And so working on the kinds of problems that I do now, which are related to catalysis and, energy needs, new materials. This is something which is a little more connected, I think, to society's needs. And so I feel a bit better also. I feel I'm using my science to address society's needs in a more direct way. This doesn't mean that I feel people should not at all do high energy physics or should not at all do astrophysics. I think those are also very appealing. There's something about human nature which makes us want to understand, where do we come from, where is our place in the world, those kinds of things. But that's not what I want to spend my efforts on.
Okay, here the twofold ones. I mean, we would like to have more understanding of what you do, but before that, a general question is, I mean, you told us how you picked this field of study, but how there are many students who don't know what they should pursue once they have an admission. They don't know what subject they like. People are typically lost and somehow they end up in some group and start research. Do you have any word of advice on how one should go about picking a field of their interest if they don't know what
Okay.
to do?
So first of all, I think you should pick something that interests you. It is quite important to pick something that you find appealing and you find interesting, because science is hard, and there will be times when you will wonder, why am I doing this? And if you're doing something that you don't enjoy doing, it will become very difficult to do. But having said that, my own feeling is that most of science is interesting. There isn't very much in science which I find not interesting. Like if you look at it deeply enough, nearly everything is intellectually interesting, is fascinating, has puzzles to be solved. But then different people have different aspects of puzzles they find appealing. So I think you should find something that appeals to you. But the other thing I think you should look at is career prospects as well. So my feeling is that if you do something like high energy physics or astrophysics, your career prospects will not be as wide as if you do something like material science or solid state physics, condensed matter physics. First of all, there are just a lot more jobs in these latter fields in academia itself. Plus, you have the possibility of finding jobs in industry. So I think this is something to consider. Now, when I was a PhD student, a lot of my classmates who did high energy physics or string theory or things like that actually switched to doing condensed matter later, because they felt that there just weren't enough good problems left in their fields. The problems were either too hard or just not there. And so they switched to doing condensed matter. I don't get the feeling that that's the case now. There certainly seem to be very active fields and lots of interesting problems, but I haven't kept so much up to date with those fields, so I can't say. But I would certainly, I mean, of course I'm biased, but I would certainly encourage people to very seriously consider condensed matter and material science as fields to go into. There's a lot happening, it's exciting, and you have the possibility of working in either academia or industry.
Okay, so the message there is to pursue what appeals to you and also look at career prospects which you can gather by talking to peers or professors, and consider all these perspectives before picking a program for PhD, right?
I think so.
Yeah.
But one thing I should say is it's not impossible to switch fields later. It's not easy, but it's been done, and there are lots of people who have done it.
Yeah, that's also true. You can, a lot of people even change subjects altogether from physics to bio, and
yes,
I mean, physics to mathematics and mathematics to physics. Yeah. And engineering to sciences is quite often commonly done.
Yes.
Yeah.
And for example, right now, you know, I mean, like the hot thing is machine learning.
Right.
And
right.
Everybody's going to machine learning. And these aren't people who necessarily studied machine learning in their college or whatever. They're just training themselves in it.
Right.
And I think in a few years, everybody will be doing quantum computation. And
yeah.
so we'll all teach ourselves that. So.
Yeah. Okay, so moving on, tell us about the research that you do. What is density functional theory all about?
Okay, so there are two things. One is density functional theory, what it is, and the other is what I use it for. Okay, so the basic problem in condensed matter physics or in solid state physics or in chemistry even is that you have to solve a Schrodinger equation, a many body Schrodinger equation, in that you have a system with lots of nuclei and lots of electrons. And you're trying to say, how should you arrange these nuclei and electrons so that the energy of the system is lowest in simplest language? And this is a problem for which we can write the Hamiltonian, write the equations. So there's this very famous quote by Dirac from long ago, like 100 years ago, where he said that the basic physics for all, most of physics and all of chemistry is already known. We just don't know how to solve it, the equation. So we can write down the equation. It's the many body Schrodinger equation. So these nuclei and electrons are electrically charged and they interact with each other by Coulomb interactions. We can write this equation, but we don't know how to solve it because it's a many body equation. So you may know already, even in classical mechanics, there are 2-body problems and 3-body problems and 4-body problems. So like a 2-body problem is the Earth going around the sun. And we know how to find its trajectory. That is Kepler's laws. And that's simple. If you have a 3-body problem, like the sun and the earth and the moon, it's already becomes a much more complex problem, which you can't solve exactly analytically. Now, when you have like a solid, like, I don't know, what shall I hold up? This phone stand, for example, it has of the order of 10 raised to 23 nuclei and electrons in it, and they're all interacting. And it's just too hard. Everything is interacting with everything else. And so we don't know how to solve it. So I give an analogy, like say you have a bunch of men and women in a room, and some of them like each other, some of them don't like each other, some of them love each other, some of them hate each other. And you say you have to arrange them all within the room so that globally, on the whole, you have achieved the maximum level of happiness. This is very hard to do. Okay, so you don't know how to do it because there's just too many things to optimize simultaneously. So in density functional theory, this was a theory developed by Walter Kohn in the mid-1960s. He showed that this problem can be mapped exactly onto what's called a one-body problem. So this is like saying you have a room with just a bunch of men standing, and you have just one woman, and you have to move her around within the room. You have to find her position where she will be happiest. And that is your one electron problem. And that's much easier to solve. Okay. But the amazing thing is the solution to this one electron problem is the same as the solution to your many electron problem. Okay, the way you arrange the women when you put them one at a time is the same as you would get if you were doing all this many people in the room at the same time.
So materials are like they exhibit a collective phenomenon or ordering in some sense.
It is not to do with the collective phenomenon. It is that there is a weird mapping between the many body system and the one body system. I mean, it is not that there's some joint collective behavior. There's still the many body behavior. And I mean, to make it more complicated still, we know that there's this mapping, but we don't know what this mapping is. It's what's called an existence proof, that such a mapping is exactly possible, but we don't know what the mapping is. But the fact that you know that it exists already helps you to start trying to solve the one body problem. And so people have very good guesses for what this mapping is. Okay, so that's what density functional theory is about. Okay. So I could also explain why it's called density functional theory. I think that's too complex and irrelevant right now, so I won't explain that. But it's a tool. So what does this tool tell me? It tells me if I have nuclei arranged in certain ways, and I put so many electrons there, I will know what is the energy of this system. If I change the nuclear positions, the energy will change. Again, I can know the energy. So this way, I can know, for example, what is the structure. Like if I have these nuclei, what crystal structure will they take? Because I just have to move the positions till the energy is lowest. So it's a tool for me. Now, what is it a tool for? It's a tool to make new materials. So you know that in history, we have the Iron Age, the Stone Age, all that.
Yeah.
Because they had these new materials that they started using. First, they used stone, then they started using iron. Now, what to me is I'm most fascinated by is what's called the Bronze Age, because bronze is a material that doesn't exist in nature. Bronze is an alloy that you make by taking copper and tin and mixing it. So that means people already then, in prehistorical times, knew that they could make this new material and it would have superior properties. But the question is, how did they know it? We don't know how they found it. Maybe it was an accidental discovery. Maybe they just tried many things. So through most of history, all these new materials we've had, people either just kept trying until something worked, or something happened by accident and they found it. So now what we want to do is what's called rational design of materials, where you understand why, if you arrange these elements in this atomic structure, the material has this properties. And once you understand that, which is where density functional theory helps you understand that, then you can say, okay, now I want a material that has certain properties, like it's super hard, or it is a very, very good magnet, or it's very reactive, or it's very unreactive, whatever you want. Then you can design on the computer a material that will have these properties and say, I want so many atoms of this element and so many atoms of this element, and I want to arrange them in this way. And then once you have checked it on the computer, which is what I do, then somebody in the lab can make this and check if that's really correct. So that's
so you propose how to construct new materials. If I tell you that this is the property I'm looking for, then you have intelligent ways of giving a recipe for that material.
Exactly. Okay.
Now there's this a naive question, which is, how do you know that your theory is correct? How do you test the theories apart from experiments? Because most of the time it's not possible that every material is tested. But what is your best, like, when are you happy with your theory?
So I would say the ultimate test is always the experiment. Okay. So I think that's true in all of physics. I mean, physics is ultimately an experimental science. And sometimes you have some beautiful theory, everything seems self-consistent, but then it doesn't match experiment, and then it's terrible. You have to just go back to it again. That's the difference to me between physics and mathematics. Mathematics, as long as everything is logically self-consistent, then it is correct. But in physics, I think that is what makes physics physics. But it ultimately has to agree with experiment. And it could be, of course, that there's some factor you didn't know about, like the experiment had some impurity you didn't know about or something. There's some factor you don't know about, which is why they don't agree. Or your calculation could have a mistake. You made some assumption that was wrong, etc. But the ultimate correctness, according to me, is always that you have to agree with the experiment.
So I guess that the research that you do heavily depends on computational power, because you run these
Yes.
simulations, right? So how did this field evolve in general from an era where there was absolutely no or very minimal computation to this present times? Are you like, I mean, in general, the evolution of the field, uh, the questions that you ask, is it critical, the computational power, or
So
how does
the
it?
kind of questions you can ask have changed with time because of computer power, and also how fast you can answer them have changed with computer power. Like in the early days, people could, the system size and also which elements they could treat depended, were limited by computational power. Okay. And now that is, we're constantly pushing the boundaries. In the early days, people also use their cleverness to make a lot of approximations and techniques which were governed not primarily by the physics, but by the need to reduce the computational power. And some of these approximations we don't need to make these days. Some of them we still need to make, but some of them we don't need anymore because we just have much bigger computational power. And to do a DFT calculation, also computers have become so fast that for a simple DFT calculation, like the standard one they say is, the silicon crystal. That's usually the first DFT calculation someone, that you can do on your laptop in a few seconds. But then, of course, there are much complicated systems which you have to run on a supercomputer for many days, sometimes many months. So it depends what you want to do. Some people have even run some calculations on a cell phone.
Wow.
So.
Okay. Moving into general things, presently, as you said earlier, we are moving into the era of machine learning and artificial intelligence and things like this. So how do you see this density functional theory fitting into machine learning or AI in this scheme of things? Because this is highly computation dependent research. So do you think the tools of AI can take this field way in a different direction altogether?
Yeah, so they seem to be interfacing very well in lots of different ways. One of them is that in AI, you always need a database to train your system. Your machine has to learn based on something. Yeah. So that database can be provided by density functional theory calculations. And then when you do the testing, also you finally test, instead of testing first on experiment, you can test on a DFT calculation. DFT is density functional theory. But there are also lots of other things you can do, like density functional theory calculations are very expensive computationally for large systems, etc. And there's something which you can do which is cheaper, which is classical potentials, which are not fully quantum mechanical. But to develop those potentials in an accurate way is very difficult. And that is something you can do now much better using machine learning. There is also this whole question, which I told you, which is at the root of density functional theory, which is what is the nature of this mapping from the many body system to the one body system. All that mapping, the complexity of it is hidden in something called the exchange correlation functional, for which we don't know the exact form. And now people are trying to learn the exchange correlation functional using machine learning. So instead of having some analytical form for it or something, you learn it through machine learning. So there are lots of different ways machine learning is really transforming the field.
Okay.
It's sometimes it's a little intellectually dissatisfying, I would say, because you have, I mean, the machine tells you this will work,
Yes.
but you don't necessarily understand why it will work.
Yeah.
So that happens sometimes, or you get, or even if you do something with symbolic regression or something where you get a formula, you get a formula which tells you this is the formula that will work.
Right.
But that formula isn't derived based on physics equations.
Okay.
So for someone like me, maybe that I'm just old-fashioned,
Yes.
but that's a little dissatisfying.
It's almost like you use the phone or something, but you don't know what goes behind it.
Yeah.
Or yeah, you really know the front end, you don't know anything about what went behind.
And
So
I
Yeah, and that's fine if you're just somebody making a phone call, but if you're a
yes,
scientist,
yeah,
you're doing more than that.
yes, exactly.
I mean,
Yeah.
not knowing really makes you uncomfortable. Like,
Yeah.
okay, you function, but how?
So
But
so
I
so
think maybe it's just a new paradigm emerging of how to do science. And we just have to change our ideas of what it means to do science.
so this brings me to get to the second part of the question that you said. It's like what is it that you do in this big field? What are the questions that you ask, and how, I mean, can you tell us about them?
Okay, so there are several things I have done. Uh, one of the things I work on is catalysts. So I'm interested, so a catalyst is something that makes a chemical reaction go faster. So I'm interested in designing nanocatalysts. So nanoparticles, which are catalysts. Uh, there are many important reactions for which we need catalysts. For example, in cars, cars which are, the conventional cars, they emit carbon monoxide and various other things which are bad for us. I mean, carbon monoxide is really bad because it's toxic. You will die if you breathe carbon monoxide. And so you need a catalytic converter in the car to convert it to carbon dioxide. Carbon dioxide is also bad because it contributes to global warming, but it's not toxic in the same way carbon monoxide is. So you want to find better catalysts, cheaper catalysts. So that is something that I work on. I'm broadly speaking, I would say one of the questions I'm very interested in is how the properties of materials change with dimensionality. The properties of, so if you have, for example, gold, we value gold a lot. Why do we value gold? One of the reasons why gold is so valuable is that it's very unreactive. So unlike silver jewelry, it doesn't tarnish. Silver gets black, it gets oxidized. Gold doesn't do that. But the thing is, if you have a gold nanoparticle, you just have a few atoms of gold, it is very reactive. So the property changes from bulk gold to nano gold. So I'm interested in questions like that. Why do the properties change with dimensionality? How do they change with dimensionality? Can we exploit this in a certain way? Like materials that are not normally magnetic become magnetic when you have nanoparticles of them. So that's again something I'm interested in. Can I design magnets like this? Alloys. Um, so I told you that you can mix copper and tin and make bronze, but you can't just mix any two metals. Some metals just don't mix. If you make them, if you try to mix them, they'll do what's called phase segregation. That is, they won't mix. It's like oil and water don't mix. Some metals don't mix. But it turns out that at the nanoscale, if you, for example, deposit just one layer of atoms of them, they will mix. Okay, so I'm interested in that, why it happens. Like for example, iron and gold usually don't mix, but we showed that if you put just one layer of iron and gold atoms on a ruthenium substrate, they will form an alloy. And our collaborators did the experiment. Our collaborators in the French group of Sylvie Rousset did the experiment, and they found that's exactly what happened. And then we could also explain why this happens. And then this is a magnetic material. You're very interested in having magnetic materials for things like magnetic memory storage, things like that. I'm recently got interested in molecular motors and molecular rotors, which are these small molecular machines you make out of molecules which move. So I'm interested in how they move, why they move, or even if it's not a molecular machine, just like, these nanocatalysts that you have, they're small metal particles, very small, just a few atoms, put on an oxide support. That's what the catalyst in your car looks like or whatever. But they don't stay stable like that. After a while, the metal particles move around and they agglomerate. They become larger and larger metal particles, and then the catalyst stops working. So I'm interested in studying why that happens, how does that happen? And we've also found, it's interesting, the way these metal particles move, they don't just move like this. They walk, they roll, they tumble, they do all kinds of weird things. And so it's just interesting and cool, I think. So that's some of the things I look at.
So you look at even the dynamics of these
motions,
nanoparticles, and okay, it's really interesting that some of your work has translated into realizing them in the experiment. I think that's when you feel.
Oh yeah, I mean, on a few occasions, something we predicted has been subsequently verified experimentally, and that's just a fantastic feeling, I can tell you, because I told you the ultimate test is always the experiment.
Exactly.
And so you predict that if you do this, it'll mix, or if you move this, the shape of the, if you do this, the shape of the nanoparticle will change, and then somebody does the experiment and the shape of the nanoparticle actually changes. It's really nice.
Yes, because most commonly what we say is, theorists, you can do it. So because they can just write about any interaction and get anything working, whereas in an actual experiment, it's really hard to realize. But when an experiment fits into theory, it's amazing.
Yeah.
I mean, listening to all your questions that you're working on, it's extremely fascinating, and I would really love to dive into each one of them, but I guess we're limited by time. So I guess this would be the right point to shift to our third set of questions, which is basically talking about gender roles and women in science in particular. So perhaps I'd like to ask you a rather personal experience-based question. So far that you've been working in the field, can you tell us about something that you have faced, any gender-based inequality that you might have seen, or something that might have interfered in your field of work, which was actually related because you were from the female gender? Something of that sort.
Okay. I mean, there's so many that I don't even know which to pick. I think, sometimes some people, especially men, they say to me, why do you keep talking about gender? Why is everything about gender? And I think everything's about gender because the people you interact with don't forget your gender. They don't let you forget your gender. They keep reminding you. I've had, a whole range of experience. I mean, okay, so I would say the first time I became aware of it was when I said I was in the 11th and 12th standard. So I was in junior college in St. Xavier's College at Bombay. And at some point, most of the boys in my class just stopped talking to me. And I didn't know why, but I didn't even realize that it was some decision or anything, but I just felt very lonely. I was in a class, I should explain, with 4 girls and 75 boys because of the combination of subjects I had chosen. And then many years later, some of the boys said, oh, you stood first in the class in the first midterm exams. And then we all decided to stop talking to you. And so, I just find that ridiculous, outrageous, everything.
Yeah.
And then I went to IIT Bombay for my master's, and there it was about 5% women on the campus. And all the time people would make comments about women, and I've had things painted about me on the road in the campus. I wouldn't say I was, particularly traumatized or anything, because I had very good friends, both male friends and female friends, and it was supportive. Then I went to Harvard for my PhD, and I was in a class of 2 women and 28 men. So it was very much in a minority, and I've had various experiences. I'm just not in the mood to talk about some of the worst experiences because some of them were really pretty bad.
Yeah.
But it's not been easy. Let me say that. And whenever something bad happens, I get really angry. And then I try to channel that anger towards doing something for women in science, so that, something bad happens to me or something bad just happens in the world to women. I read about some injustice to women or something and I get angry about it. And then each of these things I've tried to channel that anger in a positive way so that I start some program or start some initiative for women in science, so that one doesn't feel that one isn't doing anything about the situation, that one is trying to change the situation, improve the situation, help others who are suffering. See, the experiences I've had, they're bad, but I know that the experiences I've had are not as bad as what other people have had. There are many women who've had much worse experiences than I've had. And so I really want to help them.
That makes quite a lot of sense. I guess any female who is pursuing the field of science would have sort of, especially science, because the proportion is really disturbing for females. Ma'am, but one question I would like to ask is that, do you think there is a fundamental issue here, or is it possible to resolve this in some sense? Of course, it's not a small problem. It's not something that can be changed in a day. But is there something that you think there's a grassroots problem that's actually creating this whole scenario, and if there's a way to fix it?
Okay,
does that make sense?
So part of it is there's this sort of vicious cycle that the numbers are very small. And so then just because the numbers are so small, people are not used to having women around. They don't know how to treat them. Then they start feeling uncomfortable around them, or they just assume that women are not good because there's so few women and they treat them badly. And then because they're being treated badly, then maybe more women don't go into the field, that kind of thing. But so I think there are a few people who are, really bad people, okay, who really misuse their position, severely sexually harass women, make use of their power differential, things like that. But I think the vast majority of people are not like that. Okay, and if they do anything that is in any way perceived as hostile, it stems from a lack of awareness. So there's something called implicit bias,
Right.
which is having a bias that is not explicitly articulated in your mind. It is not, I mean, these people, if you ask them, would not say women should not do science, or women are dumb, or women cannot do science, or anything like that. It is just that deep within themselves, without them even being aware of it, somewhere in their psyche, there's this idea that women shouldn't do science, or women are not good at science. And that idea comes from the environment, just not seeing images of women in science in their school textbooks, or in the movies they have watched, or in the teachers they had. I mean, constantly you're bombarded with this idea that, women should do certain things and men should do certain things. And I think we all internalize it, regardless of whether we're men or women. I mean, women are also subject to these biases.
Yeah.
There have been many studies which have showed that people associate men with doing science, and women with doing arts, or with doing housework, things like that. There's a very good test you can do online. You just Google implicit bias and Harvard, and you will find this. It's a short online test you can take. There are implicit biases for many things, but one of these is for gender and science. And if you take this test, you may find that you have this implicit bias, and then you will probably be very shocked to find that you had it. The first time I did this test, I found I had it. Okay. So we have these ideas we're not even aware of.
Yeah.
And I think this is why we behave in certain ways which make the working environment difficult for women in science. And so the first thing is to become aware that you have this bias, and then fight consciously to overcome this bias. That's my feeling.
Just a follow up. It's one thing to do excellent science, and it takes quite a lot of effort. It's not just being concerned, but when you give so much time to doing programs and actively working, it's a completely different thing to work for the community. So you already said that it's because you're phased and you want to work for it. Yes, we all think of it at a certain level, but you actually manage to do both science and working for the community in general. So how do you do this, both of it? Don't you think it's quite stressful, or is it? I mean,
How do you
find
manage
it.
Yeah.
It is hard. I won't deny that. It does take a lot of time, but it's something I deeply believe in. And I mean, I don't want to boast or anything, but I think I do make a difference. I conduct these workshops for women in physics, etc. I mentor a lot of young women physicists, and people have told me it makes a difference. And so I feel it's worth doing. And it does take time away from my research. And of course, sometimes I feel like, oh, I'm spending so much time on this, and I could have written, so many more papers in this time, whatever. And also, it is something which I find the community is not always comfortable with. You're seen as a little bit of a troublemaker, someone who has a bee in her bonnet. Why is she always talking about gender? Why is she doing all this?
Yeah, I was about to ask you that you might sometime, when just for being outspoken, you might end up falling into trouble for simply expressing genuine views.
Yeah, so I always speak up, almost always. Like every time we get an email to our whole faculty that says, "Dear sir," I write a protest letter. Every time somebody says something in a talk that I find sexist, like I speak up, and sometimes I feel, why should I always speak up? Can't someone else speak up for a
Yes,
change? Or,
exactly.
Yeah, even that is quite
Yes.
overwhelming.
you can sort of feel that everybody is saying, after a while you have less impact, because it's like, people are just thinking, oh, there she goes again.
Oh.
you know
But yes, I find, I mean, I personally, and also from some general views, it's when you, this was another question I wanted to sort of ask, to wrap it up with, sort of to say, what is it that one should do? For instance, when I want, let's say I have a problem of some sort, I know you are the person I should talk to. But not everyone is so fortunate or lucky to have such a person to talk to, or so on. In general, not everybody in the podcast listening here can write a mail to you, but what is it that one should do or go forward when you have gender-based problems, or in general academic problems?
so I think, first of all, if you look, you can always find someone. There are people. There may not be people at your institution. Maybe you can find someone at an NGO. Maybe you can find someone in another department. Maybe you can find someone at another institution. Or for example, if you're in physics, there is the Gender and Physics Working Group of the Indian Physics Association. So there are resources available. There are people available. One thing I would encourage people to do, if they have any issues at all, is to write down for themselves. What is the issue? What happened? Who said what? On what day did they say it? On what time did they say it? Who was present? Because, see, people have a tendency to say, oh, this is all anecdotal. But if you can back up that anecdote with evidence, like, hard evidence, like, this was said to me at this time, and this place, and this person was there, and that person can back up what you said and all that, it's much harder to dismiss. In general, not for somebody who has a problem, but in general, to address these questions, I think it is very important to accumulate statistics, because I find that, especially if you want to convince scientists to change their mind about something, if you give them statistics, they find it hard to dismiss. If you just tell them a story, they say, that's just an anecdote, and they just ignore it. Like, for example, in India, about hiring, almost anyone you speak to will say there's no discrimination in hiring. But recently a statistic emerged, which was that in IIT Bombay, somebody collected the numbers and found that of those who apply for faculty level positions, 15 to 20% of men were called to give a talk, and only 3 to 5% of women. Now, that's a very stark statistic. And if I tell people the statistic, then they say, oh, then I don't know what to say. So, like this, so we need to start collecting statistics. There's this new program in India called Gati, which is trying to collect statistics. There are organizations like Bias Watch India, which are trying to collect statistics. So, because scientists are ultimately convinced by numbers. So we have to collect numbers to convince them that there is a problem and that something needs to be done, I think.
So do you see that India is changing for the good in this aspect?
I think it is changing, but slowly. There is certainly some awareness of these issues. You hear it being talked more about. There are more government programs to increase women. You see increased representation of women in committees. You know, like there's this famous photograph of the directors of all the IITs, the ICERs, the Minister of Science, etc., etc. It's a picture with maybe, I don't know, 50, 60 people, and all are men. And at least everybody started talking about the fact that, oh, they're all men.
Yeah.
Whereas a few years ago, they wouldn't even have talked about that. So at least the awareness is increasing.
Actually, I never thought of it. I can't think of a female director of an institute.
Exactly.
Yeah.
It's not a very comfortable.
No, there are some, like the SN Bose Center right now has Tanushree Saha Dasgupta as the director, and the Director General of CSI right now is a woman. So there are a few, but not many at all.
Okay.
And but so now, you know, the Indian Institute of Science has put out a call, an advertisement to hire faculty, and that call is only for women faculty members. So there are changes, but my worry is that there will be a backlash against this, because a lot of people don't understand the need for these changes and these new programs and things like that. So it's not clear to me that it'll be, you know, a monotonic improvement. There may be some steps back as well. So I don't know how it will go.
So I guess it's important for the women who exist in the community to sort of back each other up, and sort of create programs to get more women in.
Yeah.
Yes, but as I keep saying, it is even more important for the men in the community to create these programs and back women, because there are far more of them and they have a stronger voice, and it shouldn't be left to just the women to do it. You know, I mean, this, I think, is a real problem, that people see this as a women's issue. It's not a women's issue, it's a community issue. Our whole scientific community has this problem which has to be solved by the community as a whole. It is not something that is just a problem for women. So, and until that awareness comes, I don't think we'll see real change.
That's quite right. I hope it's around the corner, and at least we get to see a part of it. Yeah, because I mean, the kind of issues that you are talking about, which you faced in your time, are very similar to what I've faced in my undergrad also. Like, you know, you see the same difference with 6 people in a class of engineering, which has 60 students. So its scenarios more or less seems like to be the same. And people have a similar mentality still, even the youngest generation that we're talking about, who've been raised to apparently have modern thinking.
Yeah, so the IITs now, I think, have a quota or whatever, that they have to have 20% women.
Yeah, females.
And
I see.
And among students. But you check this numbers and they all have exactly 20% women. So
I mean, that just proves that it has always been less than 20, and that's like the least they could do for it.
Yeah. So I mean, nobody even has 21%. So
that's a lot, like doing the homework because you have to do it, and
supposed to meet the expectation, but just the expectations, not more.
Yeah, exactly.
I mean, the underlying message has not been conveyed properly. It's
and I think this would be a good point to wrap it up. Unless, of course, ma'am, if you have something to add, maybe anything to add to this conversation. Or...
Okay, I just want to say something in conclusion, which is I'm a bit worried that I might have given a somewhat negative message. And I want to say that on the whole, my experience has been good and has been positive. Okay, that I feel really privileged to have been a scientist. I have enjoyed my career. I've enjoyed interacting with my students. I've enjoyed interacting with my colleagues. You know, I have a really supportive circle of friends and colleagues throughout the world almost, you know, who really support me. And I think, so that's been really wonderful. So the fact that, you know, I say, oh, but it's been difficult or I have to fight, doesn't mean that the overall experience is negative. I would say the
Yeah.
overall experience is overwhelmingly positive. But on the other hand, I realize I come from a position of privilege. I come from a relatively wealthy background. I had a father who was a well-known scientist, etc. And I realized that not everybody may have these advantages and these privileges. And so I feel one has to fight to make sure that everybody has as good an experience.
Yeah.
Yeah, so it was really a nice session talking to you, ranging from your experience of being from. Yeah, I do agree that this is quite unusual to talk someone from such an elite background, but still there are ups and downs. It doesn't really mean that just because you're from an elite background, things are smooth. It's not at all so. And listening to your part of the story of ups and downs and your journey, and then to get a glimpse of your research field, and then also to address the concerns that you have for the community. It was really nice knowing you as a person. As I was telling Shreya before, that it's always very jovial to talk to you and just listen. And there is so much to learn, and that's what it was all of it today. Yeah.
Thank you, Davla. Thank you, Shreya.
Thank you.
Thank you so much for joining us today, ma'am.